Hello everyone. Let's see details of the paper titled Modeling Effect of Lockdown and Other Effects on India COVID-19 Infection Using SEIR Model and Machine Learning. This paper is authored by Satyanarayanan Sambat and Joy Bose. Suspectable exposed infectious recovered SEIR model is widely used epidemiological model to predict the rise in infection. It has been widely used for COVID-19 too. Original SEIR model is like simple. It don't account for factors such as lockdown, vaccines and reinfections. We look at modifying the SEIR model to account for these factors, then validated our model with India COVID-19 second infection which happened during April to June 2021. Figure 1 shows the original SEIR model. It has 4 blocks: suspectable, exposed, infectious and recovered. And it also have 3 important parameters named beta, which says like the transition probability from suspectable to exposed, and then a sigma, which says the transition probability from exposed to infectious, and gamma, which says the transition probability from infectious to recovered. The assumption is people stay in one of this block, and then the population remains same throughout the time, and it sums up to n. The figure 2 shows an improved version of the SEIR model with critical cases and death. During COVID-19, not everyone infected gets recovered. Some people reaches critical state and then they die too. So people in infectious state move to critical state with a probability prob I to C, and when they are at critical, a fraction of the critical people with probability prob C to D dies, the rest of the people gets recovered. This is a more accurate, better model than the original SEIR model. A more accurate model is proposed by us, which is shown in figure 3. It introduces 2 other transitions. From the suspectable, people who get vaccines, they directly reaches the recovered state instead of going through exposed and infectious state. Also, COVID-19 have second infections. So recovered people, a small fraction of the recovered people can also become suspectable, and hence they can get exposed infectious too during the second infection. This slide shows SEIR equations for the model shown in figure 2 in the previous slides. Time in our case, time unit in our case is a day. For each day, the change in the value of each of the block SEIR is given as an equation here. For example, if we took like change in the suspectable ds by dt, in a day I minus beta is by n, number of people will move from S block to E block. And if similarly, similar expressions are given for other blocks too. If we notice R0 expression, it is a smooth step curve transitioning from low to high with a low value of R0 end and high value of R0 start, and the transition happening at T0. We modify the expression for R0. So in our case, instead of considering a step curve, like we considered a smooth rectangle function which stays low when there is no infection and smoothly rises to an high value when the spread is high, and it stays high, and when things are back to normal, it comes back to the lower value. In our case, we considered 2 waves, R0 wave 1 and R0 wave 2, and the general expression for R0 wave I is provided as similar to the previous one with the additional parameter AI and BI. It starts increasing at the point AI and it stays high for the duration BI, and then it comes back to the low value R0 end. So in our proposed method, we considered 2 waves, wave 1 and wave 2. This can be easily extended to accommodate 3 or more waves too. Here, rec is the proportion of population recovering, including the vaccination effect. So if you see, V is the number of people who get vaccinated in at a time t. So the recovered expression is modified to have V2. So it have three important component, gamma into 1 minus prob I to C, which represent people moving from infectious to recovered state, and in the other component represent people moving from critical to recovered state, plus V who directly moves from susceptible to the recovered state. To introduce the effect of second infection, a variable named R-sus is introduced. The susceptible expression is updated to have like that actual component minus beta ISV by n plus R susceptible into d rec by dt. R susceptible is a value between 0 to 1, which represent a small fraction of the recovered people became susceptible again. The dr by dt represent the people who recover with permanent immunity, which is like 1 minus R susceptible into d rec by dt. We took India COVID-19 data set from John Hopkins dataset and in vaccination count from CoWIN web portal, and use LMFit to fit the mortality reported in the dataset with the predictions made in our with our model. With variables involving R0, the variables like AI and BI and K are used to adjust the values of R0, as well as probability I to C and C to D are the variables for the LMFit, which are modified to best fit the dataset. We can see visually see the best fit as well as the actual data in the image shown in the left hand side, and then right hand side image shows the R0 value, dynamic value, which transition from low to high during which have two pulses, one from April to July 2020 and the second one from April to May 2021, representing two different waves. The figure shows number of people in each of the 5 blocks over a period of Jan 2020 to July 2021. You can clearly see people in susceptible going down as time progresses and in recovered block increasing over the time. The table reports the metrics of curve fit. To conclude our work, we propose few modifications to SEIR model to accurately model the numbers for COVID-19 pandemic for India, considering factors such as lockdown, vaccination, and second infections. We have fitted our modified SEIR model with the actual COVID-19 data and obtained good results. In future, we plan to extend our approach to have different models for curve fitting and other machine learning models for regression to improve the accuracy. We also plan to implement the method for different states of India rather than taking India as a whole. The key references are mentioned here.